Can I capture you all in the video once? Just to have. One. It was very spontaneous, involuntary. How the should was on. Will it? Oh. Ah, there. For a moment, I will rotate. There. Right. I won't do this all the time. Just once we should have it. Oh, but the rotation is. I'll have to set this, take a few minutes. And you didn't mind the full screen. Or full screen on one.
It's okay. No,
Full board on one, that's okay.
that's okay.
And fast.
If confusion, we can stop and jump.
Yes, yeah. Tell me whenever that happens, because I pay attention to. Okay. It's not bad. Blank sheet. So, when is the homework due? Help me. Okay. So there is a homework one that is due today. And mailbox, right? Hopefully you guys got that idea. Homework 2 is due 6, I guess.
Yeah, next Tuesday.
Try to make sure that you understand homework 2. That will play an important role in the next few weeks or probably the half the semester or more than half the semester. So it's the most important. It's like saying in calculus, you want to make sure that you know how to take derivative, right? It is in fact, it is called functional derivative. It's different, but closely related. So it's an important homework. So I gave a lot of examples. And if you want a textbook, I haven't seen very good textbooks on the material, but there is Gelfand and Fomin. There is a link I have given in the website. And if you notice in the website, I have given some references, about 5 or 6. Hopefully, most of you got a chance to look at it. It says available in archive. That archive, I have given a link. That link is directly to the book. So it directly goes to the book. It's not just I mentioned available. I think it is okay. It's not my problem. I think archive is maybe making it available. I don't know how much copyright issues are there associated with it. Many of the books are old, so hopefully it is not, even if it is being violated, it's not a big bent on the income they are having. But surely Gelfand and Fomin is a good book. Gelfand is one of the leading scientists from the Russian school. So there's a big school following. So it's kind of a very good group then. So, and it is written by a student. I think Fomin is probably one of those student, but Gelfand is it. Yeah. So check it out. But I'll try to cover as much as needed in the lectures itself. That should be sufficient. Meet me, that's a best. I mean, if you first meet me, and then if I'm not able to help, then books, but usually books are nice, yeah, very nice.
What was the name of the book?
Gelfond and Fomin. That is Gelfond. And it's called, I think, calculus variations. The ideas we use are there in every classical mechanics book. Like Goldstein and any, let's say, Landau and Lifshitz and all that. But most of the time when they do variations, they make constant variations. So it's technically not correct, technically, right? So, but they do accommodate that and they argue and they get exactly the same thing. That is sufficient. But this is, we are doing a graduate level course. We can, why not do it the correct way? So that's only for simplification. The other books do it. They get most of the information there is perfectly okay. And yeah, Goldstein is a great book. So, nothing against Goldstein at all. It's just a small extension we are making at the general language. Okay. And then the midterm. Help me, February 22nd.
Yes.
Pretty close to. Okay. Can you see the proposal? Oh. Anything you guys want to? comment? Okay,
We are good now.
we had,
We are good now.
Yeah,
We
okay.
did arrive the question only.
okay, homework is going well. Homework one,
Yeah. Yeah, I have to plot the graph. I'll do later on today and then.
yes, and plotting not by hand.
Yeah, that's why I didn't.
Yeah.
Make the brain tapes.
Yeah, let's just make it a practice. I won't seriously take off points if it is not on computer, but I encourage you guys. This is the time to learn to do it. So, okay. So we did, let me a little bit review what we did. So we talked about Fermat's theorem and Snell's law. Is it too small? I'm writing
No, it's okay.
readable.
In this video, it's a little small. I think we can read that.
Okay, I'll try to pick it. Yeah. Right?
I think we can.
It's a little small.
Oh, it is a little small. Okay, I'll make it.
But the video, you didn't use small like this.
Yeah, that's what. So yeah, I'll make it.
We have to make our laptop very close.
Yeah, okay. So what's the difference between Fermat's theorem and Snell's law?
Snell's law is,
Used to derive the Fermat theorem.
Snell's law implies Fermat's theorem or Fermat's theorem implies Snell's law? Yeah, Fermat's theorem implies
Yeah.
Snell's law, right? It's like Newton's equation and Lagrangian or action principle. You can say that both are fundamental, but you say that, okay, one implies the other. So then there is some more insight into what might be, how nature is behaving, if you want.
You
So,
could use Fermat's theorem to solve for Snell's law.
it implies, so Snell's law is sufficient to work if you're doing optics. Snell's law pretty much gives the results. But then you realize that, oh, light has some fundamental feature that it tries to minimize the time it takes to go from one place to the other, which sounds much more interesting than just n1 sine theta 1 plus is equal to n2 sine theta 2. So one is just seems like a law The other one seems to be nature trying to do something associated with it. And we said, we had stratified, like, we talked about stratified medium. So let's say this is x1, that's x2, that's x3, and we keep going. And if this was n1, it's n2, that's in between, like in between this region is n1, n2, and so on. And at each intersection, or maybe I should also put in light starts from someplace. So this is x1, y1, and it goes x2, y2, and so on. All right. And somehow, the idea is that if you want to minimize the time it takes, then all this implies that n1 sine theta 1 is equal to n2 sine theta 2. But of course, there are many of them, so you would say ni sine theta I is equal to ni plus 1 sine theta I plus 1. When you think of it like that, you can think of, say, this is change. This is delta often is represented for a change. So change in ni sine theta I1. Right? By this, I mean this minus this, right? Take an interface, do the +1, do the or do one side and minus the other side. That's equal to? What will that be equal to? Zero, right? Because if I write this as minus, then that's equal to 0, right? And I'm saying this minus this, it doesn't matter.
Equal, then that makes it 0.
Correct. So that's equal to 0. Now I want to generalize this, or maybe before I should say, so this is Snell's law in principle, but what we have said is that if I were to talk about the time, total time the light takes, it is t1 plus t2 plus so on. So the time taken for it to go from x1, y1 to x2, y2, that's that is being minimized. So what I would do is time is the distance it takes, correct? So that's your s1 if you want. So it is s1, right? And distance by the speed of light. So that's c. No, the speed is s1, so it is v1, right? So the speed of light in that particular medium. And that's s2 over v2 and so on. But then you would say, I want refractive index somehow, so I multiply by c everywhere. And then I say this is c times t. Right? And what it depends on, we try to keep everything the same. So we keep extreme ones, we don't change at all. So that's given to us where you start from. So these 2 points are fixed. That's kind of given. By fixed, I mean, you're not changing this. So we're asking if you want to go from here to x n y n. So this is also fixed. I guess like saying if I have a ball going from here to there, those 2 points are fixed. What's the trajectory it will take to go there? And we're talking about the trajectory of light. And since x2, x3, x4 are all fixed, like we're saying, it is stratified medium. So it is y1 or y2, y3, y4, that is the variables. So the things that this depends on is y2, y3, and so on. Right, those are the variables that depends on. So I can write this as, so c t y I, right, where I represents, I can say it is 1, 2, 3 to n, but the idea is that 1 and n is fixed. Right? So there's, let's say this is 1, 2, and so on. Right, so this is the notation now. Like most of what I do will be, think of it as a prescription or a rule, but it comes from from nice principles, I will try to illustrate that, but it's like derivative. Derivative has a very deep concept in it. But as a user, most of the time you just go by the rules, right? Derivative of sine x is cosine x. You can derive it, but often we are just using it as a rule. So that's what I want you to keep track of. There are some rules that I will be providing to you. Try to capture that, and I'll go over the details and give the fundamental ideas there.
Okay, I have one question.
Yes.
We have to start from 1 or 2.
Let's start from what, okay, let's start from 2, since there is a confusion you raised, so let's start from 2, doesn't matter.
Because the first one is fixed. then
First
we
one
have
is
the-
fixed, so I mean, what that means is that I can always write it there, but then it doesn't have any dependence on it.
Because we are moving from first, yeah.
Yeah, it is like saying, I can always say gravity is dependent on z. So gravity g of z is a function, it's a constant, so it doesn't have any dependence. But I can always put it as a variable that it depends on, so this is a function, but if I vary z, this doesn't change, right? So on the right side, it is not there. So in that sense, I can always put in y1 just to make it a general statement. But if I don't, if I keep this fixed, there is no dependence on the right side, so it won't have anything to show on the right side, so that's fine. So that was the reason why I was trying to keep it, then you have this nice feature that is 1, 2, 3, and I can say why I use 1, 2, 3. Is that okay? So maybe now that I have given you a justification for that, now I can put it back
Thank you.
in this, okay? So I runs from whenever I say yi, that means that I goes from 1, 2, 3, and also it is not just one. So it's, can think of it as components of a vector if you want, right? Y is a vector, and and this is equal to summation of I going from, so let's say j, right? Because I've used I on the side, so this is 1
Yeah.
to n, and this is n I and S I. About. And you can expand Si, and you, if you want to minimize it, you take the derivative, right? That's what we did. So if you minimize this quantity, if you take the derivative of this as a function of yi, each one, this gives you the Snell's law. Like there are many derivatives you take and you get that. Okay, that should be clear. Now I want to generalize this. And the generalization we want to make is that this is discrete. But often if you're talking about an atmosphere or a general fluid medium, these are continuous, right? It doesn't have to be discrete. You don't have to be having 1 centimeter of one medium, 1 centimeter of the other medium. In solids, probably it's easy, but in gas and liquid, maybe it is not. So we want to have a continuous feature in this, and again, remember Lagrangian is a function of time, so there it is a continuous parameter that is coming in. That's what we want to lead to. This is just an example we are using to understand that. So now we want to say there is a medium where this is n as a function of x. So what's the leap I have made? Notice that,
Okay, I have one thing.
yes,
Yeah, we are running our summation from J, then is a NJ or NI?
nj, yes, good catch. I was thinking in my head, but j. Thank you. Thank you. Yeah, good catch. So this is, since I write j, it should be j, but it's a dummy variable. This is also a time to point out, once I write a summation, it doesn't matter whether I write j, I, k, anything I write is okay. I did not write I specifically because I've used I on the left-hand side, so it seems to have some significance on the left-hand side, so I didn't use it on the right side, but here I can use anything. At this stage, I can change it also, so good point. We brought that out. Okay. So how will so my idea is that I would like this to be a continuous this feature, and here the variable will be x in that case, right? So how do we make this leap? So x1 x2, x3. So this is like an I, right? There is an I is the, so here what is running is I, right? So I is equal to 1, 2, 3, right? So that's what is running when it is discrete. But I want to make this continuous. So what that means is that xi can be now changed to x. And whenever I see xi, I make it an x, and now it's not x1, x2, x3. X is a real number now, right? It's a continuous variable. That's the leap I'm making. So xi becomes x, and then that would also means that yi. Notice y was dependent on xi. For every x1, I have a y1. Or for every, or for a x1, there is a y1, x2, there is a y2, x3, there is a y3. So yi depends on xi. So this will become y dependent on x. Right? Earlier it was depending on I, so now it depends on x. That's a function now. Right? Y is a function. So the main difference we are saying is that yi has gone to a function, right? This is the leap that we are going to make. This can be thought of as the components of a vector. This is a function. In that sense, you can say a function is an infinite dimensional vector. If you imagine y of x, each of that as a component, then this has infinite components where the value of the function are the components. If you want, you can think of it like that. It will help you in the analogy that I'm making. Is that clear what I'm saying? You want to put me out?
Yeah, explain again.
Okay.
please.
So let's say that y as a vector is equal to y1, that is some e hat, that doesn't have to be a unit vector, plus y2, e2, and so on. Right. In this way, you can imagine that these are the components, like yi that I'm writing, are the components of a vector. These are discrete, that could be infinite vectors, but they're discrete. They're countable number of components in y of x, I can say, is equal to y of x itself. This is a vector, right? Not x, no, it's a vector. So this is a vector again. This is now y of x. Instead of doing summation, I'm going to do e hat of x. And this time I'll do an integral of x. Maybe this helps. This is yi times ei. That is I is equal to 1 to n. This is a discrete set of components. This is a continuous set of components. That's the only difference we are making. So for all intuition purposes, you want to see y of x as components. That's the main feature I'm trying to convey.
Okay.
Any questions on that? Just on that analogy. Okay. And you can go from, let's say, x initial to x final, let's say. Here it is x1 to xn. I can go from x initial, or maybe I is not a good variable, right? Let's say x1 to xn again. Right. The only difference is that earlier we went from 1, 2, 3. Now we are doing continuously. That's the big leap we are making. That's what we need if we want to do this as a continuous variable. Okay. If that is the case, so now I have a function. Earlier, what I was telling is, notice what we are doing here, we are trying to minimize a quantity, the time, as a function of y1, y2, y3, and so on, or y2, y3, y4, and so on. What will I minimize here? So let me write this down. So there is a time now. Right? Time taken, so this is the medium, right? Maybe I should say this is a medium, so that's x1, that's here xn. This is a continuous medium. And light goes here continuously. Here it is going in jumps, right? So this, and so on. There is a abrupt changes. So now this will go continuously. Correct. So that's the difference that is going to happen. How will I write my T here? So here it was T1 plus T2 plus T3. In the continuous space, how will I write my T?
If the one is continuous, that should be some, like a some time for all of them Tn.
No. So this will be written as summation I, like Ti if you want, or Tj or Ti, like, so there's no T. Right, that's how you would do. What's the thing on the right side you would do?
Time.
Total time, what is that equal to? Integration of,
Y X,
not yet y of x, this is just time t. So here, this was the time to go from 1 to 2, 2 to 3, and so on, so this was finite, right? Now I will say infinitesimal, correct? So dt. So I break this into tiny elements. Right, so this will be dt, so this is x dx if you want. Right, this is instead of x1, x2, x3, I'm going here dx, so there is a small dx element and we are going from on the left side of the dx to the right side of dx, right? That's the process we will say. So this will be equal to dt. Like how much time is needed for each one of this, which is tiny time dt, and I'll go and integral to it, and it will be T1 to Tn. If you start, like you can say this time is 0 in the beginning, 0 to some n, correct? So that's how you would do. But dt now, you have to so T1 was replaced with S1 over V1, right? Distance it took to so this is your S1 and the time taken is T1 and the velocity was V1. So now what is the statement here? This is ds, right? So there is a tiny element here. This is dx. But you don't have to go horizontally, right? Light might be going at making an angle. This will be ds. That's dx. And that's dy. Any triangle, so you can write in rectangular coordinates dx, dy, and the hypotenuse, we are calling it as ds. Now, light is going along that path, so it is ds by dt is speed. That's the velocity of light at that point. Right, velocity of light in this infinitely tiny element, so you can define a velocity at every instant if you want. So this is the velocity at that instant divided by c, so that you have refractive index, so that there is c times dt. So you can say c times dt is equal to refractive index times ds. Clear? Right, so dt now, if I put a c there, so I multiply by c on both sides, just so that I can get the c dt. So that's equal to refractive index n, which is now a function of x times ds, where this goes from, let's say, x1 to xn. Any questions there? It's the same idea I'm taking, but making it infinitesimal statements I'm making, and I want to start using this. Somehow I have to see y of x and other things coming in. Okay, clear?
Yeah.
1 over C ds dt.
1 over c.
Yeah, where does the 1 over C in that come from?
Oh, right, okay, so I want to use refractive index. Remember, refractive index is c over v, right?
Yep.
So that's refractive index. So somehow I want to say, so what we had was this, right? Speed is velocity. But I want to write in terms of refractive index instead of velocity. So I introduced a c there so that I can talk in terms of refractive index, so I have to put a 1 over c there also. So that means that 1 over c ds by dt is equal to 1 over n, right? That's what that is. Here it is dt that is showing up, so I want to separate out dt. So dt would be equal to n times ds over c. That c is going to show up everywhere, so I'm going to just multiply by c everywhere.
Yeah.
So then we have a clean statement that is n times ds, not dx. It is ds, right? The s is tangent, it does not necessarily the horizontal line. Clear? Same idea as here, this is a, or we, yeah, same idea here, right? S over v1, then this becomes n times s. So this is the stage we are in, but now we have an integral statement associated with it here. Here, what we did was, when we got this statement, we wrote s in terms of x1, x2, or x1, y1, and x2, y2. You want to do the same thing here? You go to the next mode. Is this readable? Maybe. Supposed to write it, right? Okay. Now c times dc is just floating around, it's a constant. Yeah.
Let's make it full screen. We can make it full screen.
Oh, here, yes. Oh, correct, good point. Slightly better, yeah. Slightly better. Here I can read. I don't know, and I'm old. So you guys probably have, but tell me, I mean,
It's okay.
tell me to
Yeah.
write bigger.
No, it's okay.
I know that I write small, unless you tell me, my tendency is to write small. But if you tell me for at least for 10 minutes, I'll write bigger. So you keep repeating after 10 minutes, okay? Yeah, don't hesitate, I won't mind it, okay? Yeah, okay. Notice again, time depends on yi, the components of this many vectors, or of a vector if you want, just yi. When you make this continuous, we said that this became a function now, right? So instead of labeling it as I label it as x, right? So this now depends on y of x. Is that clear? And the integration here is n of x times ds. And we'll talk about the ds in a minute. This is x1 to xn if you want. Doesn't matter, some initial, some final point. Is that clear? That's a generalization if you want. Okay. And there is a small flaw in this. I'll ask you again what that kind of technical error is, but we will come back to this. Now ds here is a small triangle like this, right? You would say this is dx. So for example, this is x, y, and this point is x plus dx. And y of x, so this is y of x. Oh, it's really getting small. X, y of x. And this is x, y of x plus dy. The change in y is also a function of x. Okay. And this is dy, that's ds. Okay. Which means Pythagoras theorem, property of a right triangle, dx squared plus dy squared. Y squared is equal to ds squared, right? That doesn't change, it's the same right triangle. That has to remain same. So if I want to work in terms of x, it is convenient to write dx in terms of x. So you will write ds is equal to square root. And that's equal to x plus 1 plus derivative of y with respect to x square.
C dy.
No, dy.
In the triangle, it should be just dy. X plus dx, y x plus dy.
Oh, dy, you mean that should be no x?
There should be.
What I'm saying is that so. So, okay, so this is an important feature. Let's say there is a function x and there is a y, right? That's your function y of x. That's your initial point, x1. That's your xn. That's your x, correct? So this is y of x if you want. This is y of x. The idea now is that at every point in x, at every point here, notice this could have been x1, x2, and so on. At x2, I have a y2, and when we minimize, like when we minimize, what are we doing? We say we make a variation and then ask when is it minimum? For all values of y, for which y is this minimum? So what we are going to do is that take a point y of x, so that's y of x, and I want to make an arbitrary variation. So this could be changing to this, arbitrary. When I make the same variation in this, it doesn't have to be the same, it could be different. At this point, it could be somewhere here. So the variation could be completely arbitrary. So that's y of x plus dy of x. The dy is this. That need not be the same everywhere. If it is not x dependent, that means it's a constant. Right? In principle, it can be different. And I mentioned that often in textbook like classical mechanics, Goldstein, for simplicity alone, it's not that they don't know what they're doing. For simplicity alone, that they say that it's a constant. Okay? And they are able to get the equations as they want. But in general, they do make, you have to make an arbitrary variation everywhere. Only then this whole thing works, or at least at a basic level. Is that clear? So good point. So you do want that x. So what you want to see is that this is one, this is a function, this is another function. You're adding another function to that, which is the change if you want. And that's an x dependent quantity. Clear? We'll come back to that. This is going to play an important role, but for our purposes, now I have a more concrete integral. This ds was not very clear in this statement. Now it's a very clear statement. That is an initial value, final value. There is a integral in dx if you want. I pull it out. There is a function n of x, refractive index, and there is a function say d by dx of y of x. And I have to take a square of that. Right? That's what this means, right? So I have an integral. And here we had a summation. We made a minimization of with respect to all y1s, for which y1 is this minimum, y1, y2, y3. Every y1 I try to minimize. Now I have to minimize it with respect to this function. It's no more a discrete function, it's a continuous, or it's a function, right? Earlier it was just a components of a set of numbers, if you want. Okay. On the right side, I do an integral with respect to x, correct? After I do the integral and take the limits, is it dependent on x? So if I say there is an f of x, dx, I do an integral, I calculate from x1 to x2, and let's say this is a function f. What does this depend on? So this depends on x, x1, x2. Is that correct? Is that correct? I say there's a mistake.
Yes, is only the X one and X two. That goes from X one to X two represents.
It does not depend on X, it only depends on X1 and X2. Correct. This is a dummy variable. Right, X is dummy in an integral. If I put the limits, it depends only on X1 and X2, so I cannot put X there. It doesn't depend on X. It depends on X in the sense what's the function there, so it depends on the function, but not really on X as a variable. So this depends only on X1 and X2. If you want, it depends on F also, if F is a variable. Like if F were to change, like, but typically the way we do it is that function is fixed, right, X squared. But here we are going to change that function itself. Like remember, Y of X is not known. Right, so, but we'll come to that. So I say X here. That's not technically okay. This is independent of X. Correct? But it does depend on Y though. Right, because if I change my Y, because that's what I'm trying to find, right? I'm finding the Y. So changing Y changes the time. But I cannot say X in it, right? Because it doesn't depend on X. Okay, so
Depends on X.
Y depends on X, but it is in this sense
Depends
that
on what?
F depends on X, but I do the integral and it's only the X1 and X2 depends on it. So it depends on the functional form of Y, but it cannot depend on the variable X that I choose in it because it's dummy. Right? It can depend on X1 and X2. So here I have to change this notation. So this is a function, right? So this is the way you will write a function. So now this is what a functional is. So this is T. I say this depends on Y. I don't write X because technically it cannot depend on the variable, but this square bracket means that this is a function. Okay, the square bracket now has a meaning, so this is called a functional. That means it is a depending on a function where the function can change. Here X can change. Now I'm saying Y can change, so this is Y, and it also depends on X1 and X2. In our case, we are going to keep it fixed, so it doesn't really depend on it. So I put a colon there. And this is X1 and Xn. Okay. This is called and there is a C also there, right? That's an innocent C there. This is called a functional. It's not a function. Functional in the sense that this quantity depends on a function. I can change the function. So I'm asking for what Y is this going to be a minimum? So the question we are going to ask is, so for what function? The way I'm asking means that I'm looking for a function, so I have to try all functions. So for what function Y of X is the functional P of Y a minimum, often minimum or a maximum, so it is minimum or a maximum, and often we will use the word extremum for this. So this is also we say extremum. And again, I was a little bit sloppy here. I stopped writing X1 and Xn. It is there, but in the problem, I'm not really changing this. So because of that, I say, because I keep this fixed. Later on, about few weeks down the line, we will say that actually, no, even this can be changed. And that will have an implication. Okay, all the conservation principles will come from that. First, we are going to do Lagrangian mechanics. And then we say that no, boundary also can change. This will be a boundary in time, and that will involve conservation principles. Any questions at this stage? So how do I state this? So remember earlier, what you had was, just to give you an analogy, so there was t of yi, right? This was a function, this was a multivariable function. This is now a function itself, right? I'm changing the function itself. This was equal to summation of j, and there was nj, and nj was a function of x, and this was ds, right? And that means say sj, where sj was dependent on y, let's say. This was dependent on yi. And what I did was, I said derivative of t with respect to each of this yi, or each of this I, had to be set to 0. So first I found this, and then I set to 0, right? That was my minimization principle. If you have one variable, you take the derivative and set it to 0. If you have multi-variables, you take the derivative with each variable and set it to 0. Now I have infinite variables, right? Each value of the function is a variable. I have to make a variation at every point. So that will be functional derivative. So I want to find, this will be called dt. This is a variation in t with respect to a variation in y. But y can be at any point in x, so I can make a variation at any point in x. This will be called the functional derivative. Okay. The language is, make a change in y. I don't know y to begin with, but make a change in y. If that change is a minimum, then this derivative will be 0, right? And that is that. So now we want to learn this functional derivative. So let's go and do some understanding of how you take functional derivative. We'll come back and do this problem, but let's do functional derivative. Again, it helps to think of the components, right? So let's think of multivariable calculus. So let's say there is a function that depends on y1, y2, and so on, which we will say is f of yi. When you're doing that, what you need to do is, we often think of this as x1, x2, x3, right? These are the three spatial components. That's a classic vector, right? A vector x1 plus x2 plus x3. And if I'm taking a derivative, think of a scalar function, x1, x2, x3. I'm simplifying this further, and I'm switching to x1, x2, x3 just because we are more familiar with x1, x2, x3. This is the same as derivative, a function of a vector x, right? You should think of it the same way here. This is a vector y. And what is a gradient of the scalar function of vector phi? This should be familiar. Maybe I should say x is equal to x1 e1 plus x2 e2 plus x3 e3, and the gradient operator is e1 derivative with respect to x1 plus e2 derivative with respect to x2 plus e3 derivative with respect to x3. Right. And this, when I'm taking the derivative of this, let's make it simpler. This involves, when I'm taking derivative of a function, it involves quantities like d by dx1 with respect to x1. How much is that? 1, very good. What is derivative of x1 with respect to x2?
0.
That's 0, right? So this is equal to 0. This is like saying derivative of y with respect to x in partial derivatives is 0. Right? That's the important feature. We are going to use this here also. This is d by dx1 of x3 is equal to 0. Same thing, keep doing. X2 of x1 is equal to 0. D by dx2 of x2 is equal to, what did I make a mistake? That's equal to 1.
1.
Okay, right. So d by dx3 of x1 is equal to 0. X2 is equal to 0. Equal to 1. And we say that this is nicely captured as I for any I is equal to 1, 2, 3 with respect to j 1, 2, 3. What is this equal to? I with respect to j. Now this is a
Only 2. Is
One.
IJX and IJ.
if I is not equal to j.
It is 1 if it is equal.
Exactly, right? So if it is 0, if I is not equal to j, it is 1 if this I is equal to j. Very good. And that has a meaning, right? This is nothing but, or this is a symbol if you want. This is Kronecker delta, right? So let's say this is I and a j. Don't worry about the up and down. If you have any discomfort there, put all of them down. That's okay. We won't be having too much issues with that in here unless we are doing relativity or some mechanics. So again, what does this mean? If this means this, right? If one is equal to, like these two are the same, then it's 1. If those two are not the same, it's not the same. It's not 1, it is 0, right? Another way of saying is that xj is independent of xi if I is not equal to j. Right? They are completely independent. When you take derivatives, partial derivatives, x and y are independent. Right? If they're dependent, then you have to, then you'll contribute, right? We want to make the same statement here in yi. So let's say yi. It's practically the same, yj. Only thing here, it was 1, 2, 3. Now it is 1 to n. Right? It's the same idea. This is equal to the I, j, and now I and j go all the way from 1 to n. That's the only difference, I and j also. Okay, that's multivariable calculus if you want. That's partial derivatives for you. We want to upgrade this now to a function, right? Yi and yj are functions. At each point in a function, you want to make the variation. So now let's go back and so again, summarizing. So xi and xj, or I just wrote xj to xi. Copying them again. It's delta ij. Yj, a partial derivative of yj with yi is I and a j. I have something more. Now this is not j anymore. So this is variation. So notice change in y, j with respect to change in I. That's how you define independence. Now I want to talk about change in yx. This is x represents your j. The value of y at x. How is that dependent with the variation of y with respect to another point x prime? Again, think of the plot that when Manuka was asking the question. So that's your x, that's your y, that's your function y of x. I'm making a variation at every point. So this is x. And that's my x prime. It doesn't even have to be close. That's my x prime. I make a variation. Y becomes, so this is a variation. This is. So this is y of x. This is y plus delta y, both depending on x. This is your delta y, variation in y at x, right? That's this value. This is the variation of y, right? At x prime. Oh, I should x prime, x prime. These two we are saying is going to be independent. That's the statement we are making. If we would like to do a calculus where this variation is completely independent of this variation. You could have said that, no, I want to make it a different, I want to make it a dependent variable, but we are going to make it independent. And that would mean that it is 0 when x is not equal to x prime, right? That's the statement here. Instead of saying I not equal to j, I'm saying x not equal to x prime. But when x is equal to x prime, I want that to be 1. That has to be equal to 1. Okay. This, it turns out, is very hard. You cannot get a function which is 0 everywhere and which is 1 at one point. The only possibility you can have is that this has to be infinite. When it becomes infinite, well, that having 1 is not possible. Okay, that's impossible to have a function where it is 0 everywhere and is only 1, and you have to have other constraints also, that the total change, there must be some change you need, and that has to do with the integrals. So you say that that has to be upgraded to infinity now, and this will be called, what is this, familiar?
Delta x minus x.
Good, so this is called a Dirac delta function. It's Dirac delta this, but if you expand it, it's delta. You can also say delta itself. But for practical purposes, it is just a generalization of this. This is what you want to keep in mind. Variation in yj, variation of yi, variation in y at x, variation of fx prime. Notice here what we do is make this change, and we're minimizing quantities. Here now we are making this change at x prime, and I plotted this as a function of x, but it's the same idea there. Okay. So that means I should have the properties of delta x, delta function coming in. And the property of delta function that we will need is, I think I'm going to erase this because we won't be able to come back and do this today. So we will come back to it next one. So delta function is pretty much defined by, let me say, minus infinity to plus infinity. And let's say there is a function a of x. And that is a delta function x minus x prime. Notice it is 0 everywhere. Correct. So it is 0 everywhere, right? When you do this integral, 0 multiplied by any function will be 0 unless that function has some infinity associated with it. It will be 0. Let's say that a of x is a nice function. In your homework, I have not explicitly stated that a of x is a nice function. Assume that it's a nice function. If it has an infinity anywhere, then it is shaky, right? So you assume if this is a nice function, that means it doesn't have any infinity at any point. Then you multiply it by 0, it gets killed. It becomes 0, except at this point where it is infinity, and the delta function has this feature. This is a more detailed feature. Hopefully you have seen it somewhere or the other. We'll come back and do this somewhere else in a nicer way at a more fundamental level. But here we want to use it as a user, and this is just a of x prime. Because it's 0 everywhere, it captures only that point. So for our purposes, this is the property of delta function if you want, right? Earlier, we say exponential is the easiest integral you can do, right? Exponential of x integrated gives you exponential itself. This is way more easier. Give me any function, it could be a complicated function, you just evaluate it at x prime. In that sense, it's easier. Okay, so that's your derivative. So now let's say that I have a functional. So this is a functional of y. And that's equal to minus infinity to plus infinity dx times a of x times y of x. And if you want the discrete version of it, you would say, like, it's good to always imagine, if you want to have a better understanding, this will be summation of ai times yi, right? You want j, yj. Correct. That's how this is coming from there. There is some, in some version, you will have a summation. Right? And this would be, a function would be, so f, which is a function of I. Here, you would say, I want to do the derivative of f with respect to multivariable yi, correct? And what is that equal to? Good, very good, right? So there is, what we're saying is that this is equal to, very good. So y1, a2, y2. It's a lot of them, right? At one point, I'm saying derivative with y1, it only sees this. Derivative of y2 with respect to y1 is 0. Right? All this is 0, only this contributes a1, right? If it is a2, it sees this and it is a2. When it is y3, it is a3. y4, it's a4. So you say that, oh, yi is equal to ai. But let me do this in 2 steps, okay? So this is equal to, I have to do this, right? So I actually take the summation inside. This can go inside, right? So this is aj. Aj is not dependent on y. And I have to do a derivative of yj with respect to yi. This statement is the same as this statement. And this one is a delta function. J, aj times delta of I and j. This is equal to 0 if whenever I is not equal to j. So it contributes only when I is equal to j, which means to say it only contributes at I. Right. So this is the same as a I. So out of all this, only one of them contributes, so that's only I. Is that clear? Those 3 steps. Now I'm going to repeat this in here. It's going to be the same idea. Now I'm making a change in the function f. Change in the function f. This time with respect to any value at x. Right? Think of the function y of x. At every point in x, I'm making a variation. That's the same as I take it and, oh, I should, like we had this j, right? Here summation was j and this is I, right? So when I write x at that point, immediately I should say this is x prime. That's just making it, since it is dummy, that's okay. And this is y of x. Is that clear? This is dummy. I can use anything I want. I don't want to use what I'm using on the left-hand side. Left-hand side is a function of x. The moment I take the derivative, that's a function of x. I don't want that x to be on the right side, so I changed the x to x prime. In your homework, I asked you to calculate x prime. There you don't have that problem. This is equal to integral minus infinity to plus infinity dx prime A doesn't depend on y, so that stays as it is. And it can enter the integral because this is x dependent, integral is on x prime dependent. And I have derivative of y as a function of x prime. And not derivative, variation in y at point x prime. With respect to a variation in y at x. But we said that these are independent. Only when x prime is equal to x it contributes. That means I have to use one of these delta functions there. So this is equal to minus infinity plus infinity dx prime a of x prime times delta of x minus x prime. But I know this integral because I know the delta function property, right? That's equal to a of x. But we want to be able to do this for more complicated. This is the simplest one you can have, right? This is the simplest functional you can think of. Now we want to do this for more complicated. Let's just do it quick. For your homework, a simple exercise. If you have, let's say I, which is dx, a of x, and a delta function or derivative, right? So if you have a derivative with respect to a delta function, x minus x prime, it's infinity plus infinity. You can always say this is equal to minus infinity to plus infinity dx. This is acting only on one piece. I can make it act on both. But that's not correct, right? Both are not the same. So you would say that one subtract this out, right? Whatever this is manipulated it. So make that change. Delta of x minus x prime. And I want to do that because I know the property of delta function for a function. I don't know the property of a delta function for a derivative of a delta. Like I only know this. If it's a proper function, then I do it. But derivative of a delta function, I don't know. But then we are deriving that. So now this is a function, right? Whatever this is, it's a new function, d of x if I want. It is a derivative. This I know is derivative of a with respect to x, evaluated at x equal to x prime, right? That I know is this. But what about this? You have to, this is a total derivative. That means this gets evaluated only at 2 points. Right? So this is the same as a at infinity if you want. Don't usually write this, but this is x infinity if you want. So this is infinity minus x prime. And minus of a of minus infinity times delta of minus infinity minus it. But the delta functions, if x prime here is finite, it's not infinity. This is 0. Delta function is 0 everywhere. So we are saying that x prime is somewhere in between minus infinity to plus infinity. So that's 0. That's it. So you have learned that that's nothing but derivative of a. Let's say derivative of a with respect to dx evaluated at x equal to x prime. Instead of the function, you now have a derivative with a minus sign. 3 more minutes. Use it. Let's say you have a function f of y, which is equal to dx and square root of 1 plus a of x times y of x. Or actually make it simpler first. A of x times dy by dx. Okay. I want to take the derivative. And let's say I take the derivative functional, let's see y. I want to take the functional derivative. Let me take the functional derivative at x prime. This can go through the integral. Notice what I'm going to do. This is an x integral, so x prime can get in. This doesn't depend on y. This only sees y, right? Y is all the way there. So I say this is a of x. D by dx also it doesn't see because this is x prime. It can enter the derivative. And then you say this is d of y of x. Notice these are the steps you want to keep in mind how I'm evaluating the functional derivative. X, a of x, d by dx. What is that equal to? Delta function, right? It's x minus x prime. Very good. This I now know. What is this equal to?
Minus dA of dx.
Very good, because I just evaluated that.
X.
Very good. Dx prime and a of x prime. Right. Quiz? We didn't have a question, right? Let's say
No.
f. Right? Is equal to, this is related to what we're doing in the formats, you know? This is slightly complicated than this. This is d by dx as a function of y, right? And x squared. Right. Remember the distance came in like this when we were doing Fermat's theorem. So that's your y. I want to do the same thing. I take this derivative. The only difference is that when I take a square root, I do want to do the normal derivative. It becomes 1 over this quantity, and eventually I want to reach here. And then you replace that with delta function, and then you undo it. It's a little more work, so this is quiz if you want. This is a slightly, from what I've taught, it is slightly harder, but attempt it and see what are the challenges you will face. But we'll do this next time, shortly. Attempt on this. Remember, even attempt is okay. You don't need to get the answer in a quiz. You just literally make it. Okay. We'll stop here and